Here we'll begin our study of integrals. So if I tell you to integrate something or take the integral or find the antiderivative, that all means the same exact thing, okay? So we're gonna integrate all of these functions. That's what your integral symbol looks like. And it's always accompanied with a dx or a dy or a dt. That letter will always match the variable that's inside that integral. And so when we integrate it, after we integrate it, that integral symbol will disappear and that differentiable will disappear. But those kind of go together, they're friends, and it matches our variables. It help be very helpful on our word problems. But this is our pretty easy power rule of how to integrate x raised to a power. So you remember from your derivatives that to take a derivative of x raised to a power, you multiply by the power, decrease the power by 1. And now what we're going to learn is a very simple shortcut. If you have x raised to a power, when you integrate that, you're going to go x to the n plus 1 divided by the n plus 1. So you're just going to add 1 to that exponent and then divide it by that same number. These are what we call indefinite integrals. Indefinite integrals have no numbers attached to them, and our answers will always contain a plus c. In comparison, a definite integral will have numbers attached to them. You will not have a plus c on those. We will actually integrate those and then plug in those numbers and get an answer for that. That will be a future section in a future video. But essentially what we're doing is it's like we're giving you a derivative and we're kind of asking you to go backwards to come up with the original function right there. So you might kind of know off the top of your head that, hey, this answer is going to be an x cubed because the derivative of x cubed is a 3x squared. But see, the antiderivative, that integral answer, is not unique because you could have like x cubed, you could have x cubed plus 5, you can have x cubed minus a 17. And so when you take the derivative of all of those functions, the derivative is a 3x squared right there. So which means that antiderivative, that integral is not unique, which is why we need to include a plus c in our answer when we do the integrals, when we do the indefinite integrals like this. So we got several examples here. Let's just kind of fly through it, but it is supposed to be a very quick, very easy thing. Just add 1 to that power, divide it by that same number. Eventually it'll be like second nature and you won't even have to think about it right there. Very important, if you have a constant, you're allowed to pull the constant out in front of the integral. So I can rewrite it like this. Most of the time I just carry that down anyways. I don't bother writing this step where I carry that down. But you are allowed to pull numbers out in front of that integral. You cannot ever pull variables out in front of that integral notation. If you ever pull an x out in front of that variable notation, I'm probably going to take off like 10 points, even if the problems were 4, right? That's a very big mistake right there. Can't ever pull variables out in front of that integral notation, but we can pull the numbers out. And then so if you have x raised to a power, and if I apply my easy power rule, I'm just going to integrate this, take the antiderivative of this, where I'll just add 1 to that exponent, and I'll divide it by that n plus 1, divided by that same number right there. So there's my integral right there. And then this 3 that was already there, that just carries down. Then those cancel out, and then we get the x cubed. And then just anytime you do an indefinite integral with the no numbers attached, you always got to remember the plus c at the very end of that problem. And then you could always check yourself when you take the derivative of this x cubed, you are going to get that 3x squared. So sometimes they'll be quick and easy where we can actually check that. Sometimes our answers will be a little bit involved and we won't really want to check that, but you can do that if you need to. All right, so I'm not even going to bother to take that 3 and pull out. Usually I just go straight to this step right here, right? So that's what I'm going to do right here. I know this is just a 3. This is really the integral of 3x to the 1/2. So the radicals don't really help us at all. I always change those into the exponent. And you're going to see so many problems with the fractional exponents there that I'm just going to show you a little shortcut here. So technically what you're doing, this 3 is going to carry down if you have a constant. And when you apply your power rule, you're going to go x raised to that power plus 1. So when you add 1 to it, it's like adding a 2 over 2. So that's going to be x to the 3 over 2. And then you always divide it by that same number there. So if you go x to the 3 over 2, you're going to divide it by that 3 over 2. Now, all these problems, you're going to do so many problems with the fractions. I don't write this step every single time right there. Here's typically what I'll do is I'll go straight to this step right here where that 3 will carry down. And then I know when I add 1 to that exponent, that's going to be x to the 3 over 2. And I know in my head that I'm dividing it by that fraction. I'm dividing it by that same power. And we know when we divide by fractions, you go ahead and multiply by the reciprocal. So I usually just do that all in one step there. So I go x raised to that power plus 1 divided by that same number, which means I automatically multiply it by the reciprocal, and then these 3's will cancel out. I get 2x to the 3/2, and then since it's an indefinite integral, I tag on the plus c, and then we're done. you can't like do the quotients and products separately. Okay, so you can't like integrate the top and then integrate the bottom and then divide those somehow. You know, those get a little involved with derivatives, and we had the products and the quotients there. But what you can do is make it x raised to a power. So if you see like a monomial on the bottom, you can do like a that over that problem, and then make it look like x raised to a power. So this denominator is really x to the 3 over 2. And I'm just going to subtract those exponents right there. So that's going to turn into, if I go 1 minus 3 over 2, that turns into that 5x to the negative 1/2. I haven't integrated yet, so my integral symbol is still there. Carry down that dx right there. Notice once I did this power, I applied that power, the integral symbol disappeared and the dx disappeared. But if I didn't integrate it yet, that's still there and the dx is still there. So we want to be careful with that notation. And then when I integrate this, I'm going to carry down to 5 since it's just a constant. I'm going to add 1 to that exponent. So that's going to be x to the positive 1 over 2. And then you're going to divide it by that same number, divided by the 1 over 2, which means I'm going to multiply by the reciprocal of the 2 over 1 right there. So we're going to get 10x to the 1/2. And then I got the plus c. And then we're done. And I won't care through the whole year whether you write your answer like that, or if you want to put it back underneath that radical, make that look a little bit like that, a little bit neater sometimes, and you can do that. Typically, I may do that if we have points to plug in. I want to plug in those points, and then just having the square root there make that a little bit nicer to work with there. All right, if you see like an empty integral, it's not really empty. Like when you integrate dx, you might be wondering, hey, that looks a little funky. There's just like a 1 right there. And if you want to integrate 1, that's just going to be an x. Now, when we do the derivative of a number, that's always 0 because the slope of just like y equals a number, that's the slope of a horizontal line, which is 0. But see, when you integrate and go backwards, you're actually going to get an x, because if I ask you what the slope of y equals x is, like that's like a y equals 1x, the slope of that, the derivative of that is equal to 1, right? So in general, anytime you have a number, when you integrate a number, you're just going to tag an x sign right there. Or if you have a dt problem, you'll tag on a 5t, and then you still got to remember your plus c because we have the indefinite integral. So the derivative of 5x is 5, the derivative of 1x is 1. So anytime you integrate just a number, just tag an x sign, and then you're good there. That's your easy power rule. Now, just a little thing there, I do have this little technicality for this. This power rule is going to work for us if n is not equal to -1, because when n is equal to -1, look what you run into right there. If you try to do your power rule on this one, you add 1 to the x point, you're going to get x to the 0 divided by 0, and then you're divided by 0. We know there are issues when you divide by 0, things are undefined. So the thing is, when I have this integral of 1 over x, I'm not going to use the power rule. I can use the power rule as long as that n is not equal to -1. But when it is, we're going to learn this guy in the future. There's a real easy way of how to handle that. So let's just not worry about that right now. And what I want you to be able to do, just like if I gave you something like this and said, take the derivative, you guys are so quick and just did the sums and differences separately. You just did one at a time there. I need you to be equally as quick when you're doing the integrals right there. So if you have the sums and differences, you could just do one of each, like just do them separately and then just develop a lot of speed with this because it's our easiest shortcut. And then we're gonna learn a main definition, a long way kind of next section, and then we'll learn other shortcuts, just like when we did derivatives there. We had our easy power shortcut, and then we did proc rule, quotient rule, chain rule, all sorts of stuff there. So just real quick, just fly through this one. When you integrate each piece separately, you're going to carry down a 3. You're going to add 1 to that x point, and you're going to divide it by that same number. Applying your power rule, the 5 could carry down, and you're going to add 1 to that x point, divided by the same number. All right, and when you integrate x to the first, that's just going to be x squared over 2. So you got to make sure you're switching gears. Don't do the derivative of that and put a 1 right there. You're integrating now, doing an antiderivative. So use your power rule right here. That's what we're working with this whole entire section. And then if I have this fraction, I'm going to come over to the side. So I have this -2/5. And when I integrate that, I know it's going to be x to the 3 over 2. I'm going to divide it by that 3 over 2, which is the same thing as multiplied by the reciprocal, multiplied by the 2/3 there. So that would make that -4 over 15. X to the 3/2. And anytime you integrate a number, you tag the x sign after that. You remember your plus c, and there you go. So you got to make it look like x raised to a power. Like I said, if you see a monomial on the bottom of a fraction, try to do a that over that problem. Make it look like x raised to a power. Apply your easy power rule there. So that's what we're doing this entire section. And then I made a note for myself that we need to remember the trig. So just from the past derivative chapter, you need to pause and get those down. Those are your trig derivatives, right, from our derivative stuff. And then what we got to learn brand new for us, make sure, brush those teeth, put that on your mirror when you're brushing your teeth there and study that each day, are integrals. All right, now if you think about, these are really just a reverse derivative. So like the reason the integral of secant tangent is secant is because the derivative of secant is secant tangent, right? We know the derivative of tangent is secant squared. The derivative of sine is cosine. We know the derivative of cosine is going to be a negative sign. That's why that negative is right there. So when you integrate the sine, you're going to get a negative cosine. We know the derivative of cotangent is a negative cosecant squared. So that's why when you integrate just the cosecant squared, you get a negative cotangent. Because if you did the derivative, that derivative of cotangent is negative cosecant squared, and then you carry down that negative, and then boom, you get that positive cosecant squared right there. So please memorize these as soon as possible, like immediately, right? The trig will get more involved. You got to make sure we got the basics down. I can't teach you those most involved ones, and if you ain't got the basic ones down, you're going to be struggling big time. So make sure you got the trig derivatives down. Make sure we got the trig integrals down. And then one important thing that we're going to continue our study of in this chapter is our whole position, velocity, acceleration. We already started with this. We know the derivative goes that direction. The integrals goes that direction. So now we could do some different problems with those, since we can go in both directions right there with our derivatives and our integrals there. Please watch another video. I'm going to separate this section. I'm going to make another video over solving differential equations that we're going to use in pretty much every section, possibly the rest of the year. So I'm going to make a separate video of that just in case you want to review just that part at any point in time. But that's going to start with this section as well there. So I'm going to make another little video over differential equations. So go ahead and watch that one as well. Thank you.